Okay, I think we'll get started. So today we're going to just talk in a general terms about the thermodynamics of substances in an external field, but we will use an example of the gravitational field. And this will be the only time we talk about the gravitational field in this mini course, as just an example here at the end. All right, so we start with the first law in its state function form. So du is TdS minus PdV. So that's our normal first law for a closed homogeneous system. We're going to be needing to talk about an open homogeneous system. So we add this chemical potential term. So mu dn, and I'm going to put a little bar over the top of the mu here to distinguish it from the chemical potential for the substance in the absence of an external field. So this will be the chemical potential plus the contribution to the chemical potential in the current situation, which would be in the field. Now, the field will be characterized by a generalized force, generalized displacement term. Now, this isn't completely general. This will just apply to external fields in this mini course, but it certainly could apply more generally, such as surface tension or something like that, but we're not going to worry about that. So this really fancy A is going to be the generalized force. The fancy little a is going to be the generalized displacement. And like I said, the chemical potential will be the chemical potential of the field of the substance in the absence of the field, and this will be due to the external field. All right, from here, we can quickly pick up a Maxwell relation in case you're a little bit rusty with that, or and I won't do it in full detail. I'll assume you have had some experience with Maxwell relations, and you can check out some of the other videos in the GNL project to get some of that. But we can quickly read from here. So we're going to be interested in Maxwell relations involving the field term. So if we use this expression, then we can get, say, a Maxwell relation involving the A and the T, for example. So maybe to shake off some of the rust here for you, we sort of crisscross these two variables here. So we would write something like A, so partial A, partial, let's say, S. And this is going to be at constant everything else. So constant V, A, N. These have the same sign, so they're both positive. So this will be equal to then partial T, partial A. And then everything else will be constant S, V, and N. And we'll, through the course of this series, be needing to get some Maxwell relations. We won't here for the gravitational field, but when we start talking about an electric field and a magnetic field, we're going to want to get these Maxwell relations because they're going to talk about, help us talk about like electrostriction, so the change in volume of the substance when the external field is applied. So lots of things like that. Okay, so this is one Maxwell relation that you can get from here. And if you are wanting to get a little practice with that, just see, maybe a little exercise would be to see what other Maxwell relations you can derive. Check my work here, make sure I did that correctly. Okay, well, what we're going to want, actually, is to interchange the roles of these depending on whether the generalized force is an extensive property or if the generalized displacement is an extensive property. And depending on which of those scenarios, we're either going to use the first law directly or this Legendre transformed first law where we switch out the generalized force and the generalized displacement. So maybe again here to shake off the rust a little bit, let's look at this Legendre transformation. So we're going to just define U prime. And the primes, whether it's U or H or the free energies, are always going to be the original U, H, free energies, and then minus this field term, external field term. So we do a du prime, that's going to be a du minus a d fancy A. So we can write out the du as is here. So TDS minus PDV plus fancy A dA plus mu bar dN. And then we have to use the product rule here, minus little a dA minus A dA. And so we find some things that cancel. And we are left with du prime equals TDS minus PDV minus A d fancy A plus mu bar dN, which is what we have right here. So that's the Legendre transformed, where we flip out the generalized force, generalized displacement. And we're going to need that depending, again, on whether the A is extensive, then we will use U. If the little a, so the generalized displacement is the extensive property, then we will use U. And if the generalized force is the extensive property, then we will use U prime. All right. Let's, I'll just say one more thing then quickly about the Legendre transformations. If we need to get to enthalpy or to free energy, so let's say Helmholtz free energy, then we would define that as U minus TS and go through that procedure in the normal way. And then if we wanted to get A prime, then that would be A minus let's see, fancy A. And so we could get that pairing that way. So that would be Helmholtz free energy. We might want Gibbs free energy, and we might want the enthalpy. So again, you could practice shaking some of the rust off of your Legendre transformations. See if you can write all of those down. I think in the notes associated with this, I'll have those all written out as well. Okay, so now what do we do? Well, we're going to shortcut here, and we're going to cast this U in integrated form, and then we're going to head towards a Gibbs-Duhem-like expression for this. If this feels a little sneaky to you and you're not sure where this came from, you might want to check out the mini course on rigorous thermodynamics, where we carefully go through and get to the integrated form and then talk about a Gibbs-Duhem equation. But if not, you could just kind of follow along here with what we're doing. So the idea here is we work with the integrated form, and then we just play dumb. We don't pull in the physics here. We just say, let's do the math on taking the differential form of this integrated form. So we take du, right, is over here, and then we just apply the product rule to everything here, and that's what's going on here. So you can identify each term will split into two based on the product rule. And then what we can do is we can identify this du with this du, and half of these things will cancel. And so, for example, there's a TDS term here, there's a TDS term here, so that will cancel. So du, everything over here will cancel because there's always one of these on this side. So we're going to leave a 0 on this side, and then all the remaining stuff comes over here. So this is sort of the classic way, or one classic way that one goes about getting a Gibbs-Duhem equation. So now we've got things switched such that our chemical potential here is exposed as a differential form. we can now solve for d mu bar. And here's where this idea about extensive and intensive comes in. If I bring this over to the other side and then divide by n, I get molar quantities. So the Sm, that's S divided by n, and Vm is V divided by m, and then Am is A divided by m. And so if A is extensive, we can do this. If A is not extensive, then we can't really talk about a molar quantity. We would just have that quantity over, oops, not m, sorry, n. And it wouldn't really work. And so it wouldn't work as well. So what we'll do then is if A is intensive, then we'll actually work with this guy and do the Gibbs-Duhem equation there, which is what's going to happen here in the gravitational field. Okay, so what we notice here is we get this bit, which is the chemical potential via the actual Gibbs-Duhem equation for a for the external field turned off, and then we have this external piece here that only involves the field terms. And again, these are partial molar quantities. Let's do exactly the same thing for the U prime. It's a little bit tedious here, but or overly pedantic, but we're going to be needing these, so it's very careful that we need to be careful when we get these. So let's go ahead and do a Gibbs-Duhem-like equation for this. So we take the integrated form, and notice the difference here is that this is coming in with a minus sign, and that's coming from this. And again, we just play dumb. We don't use what we know this to be from the physics. We just do the math, express this as a differential one form, and all the terms appear. Then we set this guy equal to this guy, get all of these to cancel, so we get a 0 on this side. And then we try to isolate the chemical potential over here. And we see that it's important that we made this Legendre transformation if now we are in the case that A, capital A, fancy A, is extensive. Because then we can get an expression here. So we have these two expressions for the chemical potential in terms of partial molar quantities. All right, well, that's this for the general case. And a lot of the stuff that we're going to be doing is getting into some of the details for electric field, magnetic field, and utilizing some of the fancy footwork of thermodynamics and doing Maxwell relations and that sort of thing to get quantities that we could measure in the lab, or get quantities that we can't measure in the lab in terms of quantities that we can measure in the lab. But for a quick example of this and how this would play itself out, where we don't need to do a lot of those shenanigans, we can look at just a gravitational field. So we'll have a homogeneous gravitational field, which is consider the Earth, and we're going to consider just a column of air in the Earth, above the Earth. Now this is actually, what we're going to derive is something called the barometric formula, or barometric equation, which is actually a useful thing in meteorology and other places, even though you'll see here that it's obviously a kind of a gross approximation. We'll kind of talk about that as well. Okay, so gravitational field, right? Just above Earth. So if this is Earth, then we have a uniform. If we're close enough to the surface, we have a uniform gravitational field. And that's given to us by mg. And then the potential energy is going to be mgh. So as we raise an object in a gravitational field from here to here, then we increase its potential energy. Okay, so what is the generalized force? What is the generalized displacement? Well, here's the gravitational force. So this is a real force, and this is a real displacement. So not even generalized here. So there's the real force. There is the displacement. So generalized force is mg, and A, generalized displacement, is h. M is, of course, extensive. M, the mass, depends on the amount of material. So we're going to need to go back to here and say, what did we do? A, capital A, is extensive. And so we need to use the Legendre transformed version of the first law. Now we can divide by m, or by n, and that gives us molar mass here. So here is A, fancy AM, and here is then this equation. So we're using U prime, so this guy will come here. So minus SM plus VM plus mgdh. Okay, so now we're in the specific example. This is general. Specific example here of of particles in a gravitational field. Now, let's take this to be a gas. So we'll talk about the gas above Earth here, and we'll take it to be an ideal gas. Let's see, I'll switch colors here. Take it to be an ideal gas. And here's, of course, a very gross approximation. Ideal gas, very good approximation. Gross approximation here, isothermal through this whole column of air. Now, what is equilibrium? Well, equilibrium is when the total chemical potential here is equal to, the change in total chemical potential is equal to 0. Or in other words, the chemical potential is constant throughout that whole stack of air, meaning that if we're at the chemical potential at H1 and H2 is equal, if it wasn't equal, then particles would be moving in one way or another and we wouldn't be in equilibrium. So through all this whole continuous stack from the surface of the Earth all the way up to the end of the atmosphere, we have constant chemical potential. Okay, so if that's true, then we use our Gibbs-Duhem-like equation, set the left-hand side equal to 0. We're isothermal, so we're also going to lose the entropy term, and we're left with just this, right, which is starting to get pretty simple. We'll just bring the P over to one side, right? So here is, all we've done is just bring the P over to one side, and we've put the minus sign onto, so this would be minus, and then the minus sign we put over here. Very careful to follow that minus sign. It's obviously going to be important here. And so minus sign comes in. Now, the molar volume, right, if it's an ideal gas, is RT over P, which is nice because now we have the integration variable in place. It's isothermal, and of course R is just the gas constant. So RT is constant, but P is the integration variable. So now we can integrate both sides. So we'll actually send an integral through, integrate this side, integrate this side. We're going to get RT ln P equals minus mgh, and then plus an integration constant. Well, take a couple of, well, I guess I could work this through. So that's simply, all we've done here is integrate up this side. And so now I'll have log P equals minus capital M G H over RT plus a constant. And so then we'll exponentiate both sides. So we get P equals e to the minus mgh over RT plus a constant, right? So this can be written as e times that constant, e to the minus mgh over RT. Well, what's that constant? Let's set h equal to 0. That would be this pressure at sea level. So we'll call that P naught. And so we set H equals 0, e to the c, this whole thing becomes P naught. So we have P equals P naught e to the minus mgh over RT. Right? So I think we'll stop here, but one fun thing that you could do as an exercise is, let's say you have mixed gas with different molecular weights. And they're ideal gases, so they don't interact. So you can independently work out they independently follow the barometric equation. And what you can do then is see how the concentration changes with height. So you can plot mole fraction, or start with a particular mole fraction, say 50%, and then see how that mole fraction is distributed as you go up in height. I don't think we'll end up doing that, or we won't do that in this series, but that would be a good exercise for you. Yeah, so this equation is, again, useful. Obviously, some gross approximations here, but it's one of the things that we use that atmospheric scientists use as sort of a first order or zeroth order approximation to pressure with altitude. Now, of course, the atmosphere is dynamic, so we have rising thermals and other jets and other sorts of things that are disrupting the pressure with height. And of course, the temperature drops off very severely with height, so isothermal is a pretty gross approximation. All right, so this sets the stage for us. So go through this and see if you can reproduce this with a blank sheet of paper. I certainly, it was difficult for me, certainly when I was trying to learn this, that keeping all of this straight and knowing when we use the U and the U prime, getting all the way to the Gibbs-Duhem equation. So a lot of good stuff here. So go ahead and practice that. And then we'll move on to tackling the electric field next. And then we'll finish off with the magnetic field.